For today's lesson, our focus standard comes from Grade 8 Expressions and Equations, Standard B. Explore connections between proportional relationships and linear equations. Our topic for this lesson comes from Analyzing Functions, Compare Proportional versus Non-Proportional Linear Relationships. Our essential question for today is, how do proportional versus non-proportional linear relationships compare in each of the three views? Please take a moment, pausing the video if you need to make sure that you have your header complete along with today's date. Be sure you have the standard, the topic, and the essential question copied down, as well as a question column and a note column, and resume the video when you're ready to begin. Throughout our study of linear relationships, we've continued to look at various types. And so today we're adding in two different types of linear relationships, proportional versus non-proportional. And we are going to get to definitions, but I actually want to save those for last. So we'll come back to this. Let's go ahead and look at the table I've set up to compare and contrast proportional versus non-proportional linear relationships in each of the three views. So we're going to look at graphs first, and here I've set up 4 graphs. 2 of them, here on the left, are proportional linear relationships, whereas these 2 on the right represent non-proportional linear relationships. I want you to take a moment to analyze all 4 graphs and see if you can find what makes these 2 the same that's different than these 2 graphs. What I notice is that the y-intercept for both of the proportional graphs is the origin. They both intersect when x is 0 and y is 0, right here at the origin. Whereas on these 2 graphs for non-proportional relationships, they both have a b value that is different than 0. Here we know we have a positive b value, here we have a negative b value. Neither one of these go through the origin. So in our graph view, when we're trying to decide if a linear relationship is proportional or not, we're going to focus on the origin. Proportional relationships go through the origin 0, 0, whereas non-proportional linear relationships do not. Let's take a look at the next view. Here I have 2 tables on the left that are going to represent proportional linear relationships, and 2 tables here on the right that are going to represent non-proportional relationships. And again, all 4 tables are linear. You could do some work to find the slope, the change in y, and the change in x for all 4, and you'd be able to prove that they're linear. So now we need to dive further and say, what can we see in these 2 tables, what type of pattern that would make them proportional that we will not find in these 2 tables. Again, I want you to examine all 4 tables, taking a look at the patterns in each of them to see if you can figure it out. There's a few different patterns that you can look for, but one pattern that I think is interesting is if you take the raw data, the y and the x, so notice I'm not finding slope because I'm just using the raw values from the table, it creates a set of equal fractions. So if I take the y value, which is 12, and the x value that goes with it, which is 1, 12 divided by 1 is 12. 24 and 2, if I take 24 divided by 2, I get 12. 36 divided by 3, 48 divided by 4, all of these are equivalent ratios or equivalent fractions, and they all equal 12. So go ahead and see, can you find these patterns? What happens when we compare the y value to the x value as a ratio for these other 3 tables? So again, if we take the raw y and x values, some interesting patterns happen. With the first table, they were all equivalent ratios that equal 12. And if we look at this next table, and again take the raw y value and the raw x value, 6 and 2, 9, 3, 15, 5, and 27, 9, they all set up equivalent fractions that equal 3. But look over here. On our non-proportional relationships, that pattern doesn't hold up. While they're still linear, the raw y and x values from the table do not create equivalent fractions. 3 divided by 1 is 3, 5 divided by 2 is 2.5, so on and so forth. We get different numbers as we divide the y by the x. Same with this fourth example. -4 divided by -1 from our table makes 4. We can't divide by 0. 11 divided by 4 and 29 divided by 10 all make a different value, so they are not equivalent fractions. So that is one way and one pattern that is an easy way to check if our tables represent a proportional relationship. They will have equivalent ratios created by the x and y values, whereas our non-proportional relationships will not have equivalent ratios when we use their x and y values. So the last thing I want to point out, though, with this last example here that was a non-proportional relationship is this point right here, 0, -1. We learned in its graph view that a proportional relationship goes through the origin 0, 0, when x is 0, y is 0. So in our tables, if we're given a value where x is 0, we know that the y value must also be 0 in order for it to be proportional, because all proportional relationships go through the origin. So that would have been one more clue with this table that it is not proportional because of this coordinate x is 0, y is -1, and it does not go through the origin. Let's go ahead and take a look at our last view equations. Here in our equation view, I've set up again 4 examples. These 2 equations represent linear proportional equations, whereas these 2 on the right represent linear non-proportional relationships. What do you see as a difference between this pair of equations and this pair of equations? One thing that I notice is that these 2 equations on the left that are proportional are one-step equations, whereas these 2 on the right are two-step equations. Furthermore, these 2 equations here on the left, if we think about it as slope-intercept form, because they're linear relationships, they don't have a b value. We know it has an m value because there's a coefficient with our x term. Our slope is -7. In our second equation, our slope is 1/4 because that's the coefficient of x. But then there's no b value. So that tells us it goes to the origin because when b is 0, that's our y-axis where it crosses the y-axis. It's our y-intercept. So these 2 don't have a b value because they go through the origin, whereas these 2 examples, which are non-proportional relationships, are in y equals mx plus b. Again, we can see here in this fourth example, the slope is -2/3 because that's the coefficient of x, and our b value is -5, our constant. Here in our first example, the mx plus b has been rearranged ever so slightly, but our m value is +2 because that's the coefficient up in front of x, and our constant is 9, so this must be our b value. It crosses the y-axis at +9. So, to recap, in equation form, a proportional relationship does not have a b value, where a non-proportional relationship does have a b value. So before we close out this video, let's make sure that we have the definitions. After seeing the examples in all three views, we can now define them. Our proportional relationship is going to relate two quantities, our x and our y, by a set of equivalent ratios. That was the main form that we used with our tables. So if we can create a set of data of equivalent ratios with the x and y values, the relationship is proportional. A non-proportional relationship has a constant rate of change, the m value, which makes it linear, but the data is not a set of equivalent ratios. So this is going to conclude our video for today on comparing proportional versus non-proportional linear relationships. Please make sure that your notes are complete and that you're ready to work more with these types of relationships in class.